Okay, instead of looking at chemical reactions in thermochemistry, let's look at just simple phase changes. One of the things you need to do is make sure that you know all of the names for these phase changes. In particular, make sure that you know fusion means melting. And some people know sublimation already. The opposite of sublimation is deposition. But anyway, make sure you know them all. And also, the thing about them being endothermic versus exothermic. So notice that I have these, I wrote the energy diagram. It's an energy diagram. Solids have the least amount of internal energy, then liquid, then gas. Maybe that makes sense to you because of the way they're bouncing around and so forth. But anyway, so knowing that, we know that we're going to take a solid, it's going to be an endothermic reaction to get it to be a gas. You probably really know that if you have a solid and you want to make a liquid, what do? You heat it. And that's because the substance needs to absorb heat in order to become a liquid. So it's definitely endothermic. These tend to make a lot of sense if you think about it. To make these occur, you heat the substance. Okay. The opposite is true over here. To make these occur, you cool the substance. So the opposite. The thing is, we tend to think of cooling as like adding something to the substance. I'm putting cool into the water to make it freeze. But cooling is really just removing heat. So you're pulling heat out of the water to make it into a solid like ice. So like if you have water in your freezer and you're removing heat from it, nothing's getting hot that you can tell. That might seem counterintuitive because your freezer is really cold, and when it's freezing ice to make ice, it's not warming up. The thing is, what your freezer does is it removes heat from the liquid and puts it out into your room. So your room is actually getting warmer, and you just may not realize it. So that's true in a lot of these. You don't really notice what's warming up or where that heat is going, but these are exothermic. You are removing heat from the substance to make it occur. Okay, let's look at how we can put this together. We're about to put it together with some numbers. So delta H, and we usually say for a reaction, the heat of the reaction, you can do this for a phase change as well. The heat of fusion is the change in enthalpy for melting, and heat of vaporization, change in energy for vaporizing. What if I want the heat of condensation? So what if I want this? Often tables will just list values for these two. So to get the heat of condensation, this one is going to be, I'm interested in gas to liquid. So I'm just going to take whatever number I have here and change the sign, because it's the opposite reaction. Let's look at a heating curve. So the main thing you need to get from this is that during a phase change, temperature does not change. In other words, on this bottom, what I'm doing is I'm adding heat. So I'm adding heat to the substance, and you may, think right away, well, it's going to warm up the whole time I'm adding heat. Well, that's true if there isn't a phase change happening. But if there is a phase change happening, the temperature will flatten out. So let's just say that I'm dealing with ice down here. Haven't heated it yet. And ice is not necessarily at 0 degrees C. It can definitely be colder than that. In your freezer, it's about -20. So I'm starting with ice that's very cold. I put it out into the room, and it's absorbing heat from the room. And during that time, my ice is warming up. Once I get to 0 Celsius, then it starts to melt. So so this is melting. And during this time, as it absorbs more heat, its temperature is not changing, and I'll have a mixture of solid plus liquid. Once it is all liquid, then it will start to warm up as a liquid until I get to the boiling point, at which point start to vaporize, and when it's vaporizing, I'll have a mixture. So this is vaporizing. I'll have a mixture of liquid and gas until there's no liquid left, and then of course I could heat the gas. This is a little bit of a simplification because evaporation may be happening at the same time and so forth, but this is how we kind of look at it as a simple model. So during this part, we know that when we are heating water on the stove, it doesn't just keep getting hotter and hotter. It is absorbing energy, but that energy is going to make the phase change. So anyway, that is the take-home message of this one, is that during a phase change, temperature does not change. Let's do a simple problem with some math. This one has a lot written on it already, so I'll just explain it. So we're interested in condensing water vapor, and I'm given the heat of vaporization. Heat of vaporization is liquid to gas, but I'm interested in gas to liquid, the opposite reaction, and that's why when I brought this number down here, I changed the sign. Okay, and then I've got my gas to liquid reaction that I wanted. Okay, and then it's kind of stoichiometry from there. I have my amount of my reactant. I change it to moles. This, of course, is using molar mass. And then this is the step where I use the coefficient and the heat of condensation to get to the amount of heat released. And I got released because it has a negative sign here. It's exothermic. That's the amount of heat released. Okay, and if heat is being released, that would tend to warm the surroundings. And it may be an open system where that heat is being pumped out into the room or somewhere else using a refrigerant. Okay, let's look at another kind of problem we can do. On this problem, I've used some color coding to label the different segments, because let's just say you started with ice and you're adding energy. You would do a calculation on how much heat or energy it takes using to warm it up to 0. During this phase, you're just heating ice. You would use this equation, the QSMAT equation. And then once you got to 0, you would have to look at the calculation to melt the ice. And we would use the heat of fusion similar to what we just did. Once it's all melted, then you would consider this equation to warm up the water. So the main thing is, when you're doing calculations that involve both heating and cooling and a phase change, you have to break it up into those segments and look at the energy involved in each one. The other thing is, beware that specific heat depends on the state of matter. The specific heat for ice is different than the specific heat for liquid water, say, and so on.